Now, when it comes to titration, the reason this is so high yield for your exams is, number one, you'll get a question about the methodology of titration, right? So this involves which equipment to rinse with what solutions, what type of indicator to use, and then how to interpret data that is being collected from an experiment on titration. The next kind of question you're going to get is going to be calculation questions on titration. Now, neither is particularly difficult, but both requires a really good grasp of every single step of this method. Okay, now let's quickly recap. Gerald, what is a definition of titration? Don't you look at your notes? Top of your head. Can you give me a definition?
It's finding the correct amount of base to neutralize a specific acid.
Good, but you all need to take it a step back. I want you all to realize this. Titration is not just restricted to acids and bases. Titration can be used in redox reactions. It can be used in precipitation reactions, neither of which involve an acid or a base, right? So your definition is not grounded in an acid or base. Alphys, your turn.
Wasn't it just like measuring accurate amounts of volume of a
Good.
solution?
Shorten that down. Volumetric analysis, right? And what is the goal of this volumetric analysis, Mithilesh?
To determine the concentration of a different substance that we're titrating it with.
That's it, right? So, and how are we going to do that? Through reacting it with a solution of accurately known concentration. Reset, what is that also known as? Solution of accurately known concentration. What is that called?
Oh,
Sorry, you cut off there. Could you repeat that?
It's no, I haven't said it because I can't remember it. I do remember there was a name for it. I forgot what it was called.
Mahir?
Standard solution.
Good, standard solution. All right. Make sure when you guys come into class, you've at least spent 5-10 minutes minimum revising. You should have also done the homework questions from the previous lesson, okay? Because if we want this to be an accelerated class, I can't go back and be revising the same basic stuff again, okay? So to put things together, it's a form of volumetric analysis. We are determining the concentration of an unknown solution through reacting it with a standard solution. So that is the formal definition, but it makes a lot of sense. We're using volumes, we're determining concentration through reaction with a standard solution. 3 big things I want you all to remember, okay? So underneath titration, there are many different types. There's precipitation, there's redox, and there's acid-base. So very quickly, what I'll write for you is when we're talking about titration, there are many different types. Redox titrations, precipitation titrations, and the one that you'll be looking at exclusively in this particular module is acid-base titrations, right? So that's what we're going to be focusing upon. Now, I'm going to scroll down, and we've gone through all of this, and we've gone through how to make a primary standard. Gerald, can you revise the rest of the class? What is a secondary standard?
I don't know if we went over it last week, because last week you said you would introduce buffers. That's why.
Oh, have I not gone through primary and secondary standards with you all?
No, you said this week we would start buffers. So I don't remember doing any standard solutions or anything. Yeah.
Mithilesh, did I go through primary, secondary standards at all? In your notebook, is it there?
No, the last thing we did was the buffer thing. The buffers was the last thing we did, the Henderson equation. And then we said that we'd start titration this week.
Okay, very weird. Yeah, okay, sorry, my bad. I guess I haven't gone through titration with you all then. Apologies. So many classes, my brain mixes up which class is up to what, but you're all more or less up to the same thing. Okay, sure. So we kind of left up here, I guess, then. Okay. What I'm going to do is we're going to come back to buffers. We'll touch upon buffers very briefly. Have I gone through the basic principle of a buffer? How about I just ask Riyasat, tell me a bit about what a buffer is.
Buffer is essentially any reaction or system that resists change. I think that was
and in this context, what changes it resist?
I think, yeah, it essentially obeys the Shadley's principles of changes in concentration. And
yeah, good. The basic essence here is a buffer is a solution that resists changes in pH. And it only resists changes in pH when small amounts of acid or base are added. Now, I'm rushing this because our formal notes and buffers are actually later on in the theory book, because that's how the module is structured. But just to teach you Henderson-Hasselbalch, as I've already done, I'm just going to very quickly recap buffers, right? So that's the key principle there. It does obey the Shadley's principle. Now, Mithilesh, what actually composes a buffer? What is it made out of?
It's made out of a weak acid or base and its conjugate pair.
Good. And what's a buzzword you want to use, right? Are there going to be similar amounts or different amounts of the acid and conjugate base?
Molar concentrations of both.
Good. You know what? In exams, it's good to say comparable, because equimolar is actually when a buffer is at its strongest. And I'll mathematically show this to you very shortly, right? But when you have comparable amounts of an acid, which is HA, and the conjugate base A minus, in case, just to remind you, it's a weak acid, that's when you have a buffer set up. Now, a buffer is strongest when you have not comparable, but equimolar amounts of the acid and conjugate base. And the way you'll understand that is go back to Henderson-Hasselbalch equation. What is the Henderson-Hasselbalch equation? What's the equation for it?
Oh, sorry, you lagged out for me. Can you repeat it?
Yeah, Henderson-Hasselbalch equation. What is it?
Can't remember it entirely. But wasn't it something to do with the pH and how it equals pKa plus?
Gerald, what's the Henderson-Hasselbalch equation? Gerald, Henderson-Hasselbalch equation?
It was a calculation for pH, but you would do it the concentration of the
Sorry guys, I think I cut off. Gerald, could you just repeat that? I don't think.
Oh, okay. So the Henderson-Hasselbalch equation was basically a calculation for pH, and you had pKa plus minus log 10 of the concentration of the A anion over the its conjugate pair. It was like the HA.
Good. Now it's not plus negative log 10. It's just plus log 10 of the degree of ionization. Okay, so that's the equation right there. This is important for two reasons. I want you to remember two things about the Henderson-Hasselbalch equation. It is one of the ways to find pH of any weak acid or base, right? That is one very important thing you have to remember. The second important point here is, Mithilesh, what would this equation simplify to if you had equimolar amounts of an acid and base?
pH is equal to pKa.
Good, right? And in that specific scenario, when pH equals to pKa, that is when a buffer solution is at its strongest. Okay, so that is also very important to note. So that's why a buffer is formed when you have comparable amounts of an acid and base, but it is actually at its strongest buffering capacity, aka it has the greatest capacity to resist changes in pH when there's equimolar amounts, and as a result, pH is equal to pKa of that solution. Okay, Very good. All right, we'll move on now. We'll come back to buffers, so don't want you to fret about it. Remember, the hardest part about Henderson-Hasselbalch equation is what, Mahir? Is it actual formula, or is it knowing when to use it?
I think knowing when to use it.
And Mahir, when would you know when to use it in a question?
Like, I guess when there's no other options.
Whenever you need to find pH, it's one of the ways you work backwards, right? So you think, well, pH, I can find hydronium ions, or I can use the Henderson-Hasselbalch equation to get to pH. Or I could find POH, subtract 14 to get to pH. You need to have those mental thought patterns in your head as to how to get to your answer, right? And the other thing is, whenever you get a question about a weak acid, Henderson-Hasselbalch should be at the back of your mind. Make sense to everyone? Good. All right, we're going to move on because that's nowhere near as important as titration. Okay, in fact, in the actual HSC, I can probably bet you're not going to get a Henderson-Hasselbalch question. It's more for trials. This stuff will definitely come up in your HSC, definitely going to come up also in your trials. Okay, so again, apologies for picking on some of you and expecting you to know about titration if I didn't teach it to you. But you all gave a good explanation from what you learned at school, okay, which I'm happy with. Now, coming back to this, titration is a fancy word, and we need to break it down. Now, just like how gravimetric analysis is a mass-based analysis, titration is under the heading volumetric analysis. It is a type of volumetric analysis. So what that means, actually, I've written it right here, volumetric analysis, is that we'll be using accurate volumes of solution. Accurate volumes of solution. That is very integral to the actual method of titration, right? Now, a lot of you got this correct. The goal of titration is to determine the concentration of an unknown solution, right? So when you have a solution of unknown concentration, the goal is to determine that value. The way we do this is where some of you are kind of mixing things up, is not just acid-base reactions, etc. It's through any reaction with another solution that has an accurately known concentration. So to put things in perspective, let's say we're reacting HCl and NaOH. Okay, and we're forming NaCl and H2O. So if I want to find the concentration of this HCl, I would need to react it with an accurately known concentration of NaOH, and I'd need to know exactly when they stoichiometrically react. Okay, I can't have any excess limiting reagents. I need a stoichiometric reaction. And what that involves is very accurate volumes. Do you all agree? I need exactly the volume of NaOH to react with that HCl. Now, bear with me with the mathematics here. If I know the concentration of NaOH, and I can accurately determine the volume of NaOH required, I've got C and V. Mathematically, what can I find, Mahir, if I have a C and a V value?
N.
N, right? You can find N of NaOH. And what did I tell you all? This is not a excess limiting reagent question. We can apply the stoichiometric ratio. So if I know the number of moles of NaOH, and it's a 1-to-1 ratio of both reagents, what would be the number of moles of HCl? Gerald?
1.
Yeah, it would be equal to the number of moles of NaOH, right? And so I have the number of moles of HCl, and typically I would have weighed out, or I would have accurately got a 25 ml sample of a HCl. That's typically what we do in titration. So I know the volume of HCl, which is typically always 25 ml for whatever solution you're analyzing. If I've got the N and I've got the V, does everyone agree I can find the C value for HCl? That is how easy titration is. That's the simple maths that's put into play. Now, the hard part is, everyone, how do we know exactly how much NaOH is required? Right? These are colorless solutions. HCl is a colorless solution. NaOH is a colorless solution. How on earth would we know exactly when an acid and base stoichiometrically react? Who has an answer for me? I want you to think critically. Mithilesh, what would you do? You have two solutions, an acid and base. You want to know exactly when they react. What could you add to this mixture that can maybe qualitatively tell you exactly when the solution has neutralized?
Indicator.
Exactly, right? So the goal of the indicator is to determine the volume of our accurately known concentration that actually reacted. Okay, so we'd usually determine this via an indicator. Very good. All right, so there's a few key important terms you need to understand with titration. The first important term is this term here, equivalence point, right? Now, equivalence point is exactly what I was discussing here. Equivalence point is the volume of solution that is required to react with whatever we're analyzing. Okay, and we're going to start giving names to these solutions. So if I want to determine the concentration of HCl, I'm analyzing HCl. Does everyone agree? Since I'm analyzing HCl, we call this our analyte. And the analyte is always a solution which we don't know the concentration of. Does that make sense to everyone? Right? So the goal of titration is to determine the concentration of analyte. Okay? Now, since it's called titration, we need to have the word titrate or titrant somewhere. So this solution here, the solution that we're using of accurately known concentration, is what is called our titrant. Our titrant. Our titrant is a solution which we accurately know the concentration of. Okay? Now, it's called the titrant because it's being used in the titration. But when if I just gave you a bottle, if I came to your school and I gave you a bottle of solution of very accurately known concentration, you wouldn't call that a titrant because it hasn't been used in a titration yet, right? Mahir, what did you say we call the solution of accurately known concentration?
Standard solution.
Standard solution. That is the definition of a standard solution. You would have created one up in year 11. A standard solution is one of a highly accurately known concentration. So your titrant is always the standard solution. It is a solution that you know the concentration of. Okay, very good. And so the word that I've introduced here, which is equivalence point, is a volume of titrant required to react with our analyte. It's a volume. That is what our equivalence point is. It's the volume of reagent required to react with our analyte. Is everyone with me? That is our equivalence point. And the goal of titration, everyone, is to determine this volume. Everything else is very easy. You would have already made up a 25 ml solution. You don't know this concentration, and you already know this concentration value. So the only thing you can really mess up in titration is determining the equivalence point. If you overestimate or underestimate this volume, you're going to get a completely different concentration of analyte. Is everyone with me? So the ultimate goal here is determine the equivalence point. That is a goal. That is how we will find our concentration of analyte. Now, again, there's no way to know exactly when these two solutions react because they're colorless. So we do what Mithilesh has mentioned, which is we use an indicator. Okay? And everyone, we hope that this indicator changes color exactly when all acid and base has reacted. Okay, so exactly when we have that neutralization, we hope that the solution changes color. Now, the name for the volume of solution when this entire solution changes color is called endpoint. Endpoint is when the solution changes color. And it's a volume of titrant required for the solution to change color. So both are volumes. Everyone with me? Now, the goal of titration, and I should have written it here as well, is we want our endpoint to be as close to our equivalence point as possible. Does that make sense? We want the volume of titrant that completely reacts with our analyte, this volume here. We want that volume to be the exact same as the volume required for our indicator to change color. Okay, that's not always the case. And if it's not always the case, that's going to reduce the accuracy of our experiment. Does everyone agree? Okay, so the whole goal of using an indicator is so we can observe an endpoint, a point where the solution changes color. And the goal is solution should change color exactly when both reagents have stoichiometrically reacted. Now, I know I've spoken a lot. Does anyone have any questions so far? I want this to be very discursive. Ask away any questions you have.
Does the titrant have to be a standard solution?
Yeah, so you would, in case it's always the case, you'd want your titrant to be a standard solution. It has to be one of known concentration. Because, Mahi, if you think about this, let me actually rub out some of the red. If you don't know, I'll use blue here. If you don't know this concentration, right? aka is not a standard solution, and you don't know this concentration, you have two unknowns. You go back to year 7 maths, you need two equations to determine two unknowns, right? And so it's impossible to do a titration unless you have one solution of accurately known concentration, which is your standard solution. Does that make sense?
Yeah.
Good. Any other questions at all?
Yeah. Is the equivalence point a specific pH which we're trying to achieve?
It's actually a volume. Okay, it's actually a volume that we are trying to achieve. It's the volume exactly when our standard solution has reacted with our analyte, when there's no excess limiting reagent. Okay, that tends to happen at a particular pH as well. Think about this question, Gerald. What kind of salt do we make? Because I taught us how to break down salts. Do you remember that from last lesson?
Yeah.
So NaCl, what kind of salt is it?
It's a slightly basic salt.
Are you sure it's a slightly basic salt? NaCl. I'm going to get you to break it down in front of us. Sodium. Is it going to affect your acidity or basicity?
No.
Okay, so the chloride ion, what's its conjugate?
Chloride ion is HCl.
Good.
Its
Strong
conjugate
or
is
weak
HCl.
acid?
HCl is a strong acid.
Good.
So,
What's the conjugate of a strong?
weak base.
Very weak. Not weak.
Oh,
Very weak, aka neutral. If you're stuck, this is all you have to do, Gerald. You just have to draw the equation and you'll realize the Cl minus cannot go backwards. According to your equation, it cannot go backwards and accept a proton. So it's extremely weak or neutral. Does that make sense? So this is a neutral salt. So Gerald, at equivalence point, when the acid and base have stoichiometrically reacted, there's only sodium ions, chloride ions, and water. What will the pH be?
Basically neutral. It's like 7.
It'll be 7, exactly 7 at 25 degrees, definitely, right? So that tends to happen at pH 7, but it's not always the case. Okay. Yeah, so that's the case there. So remember again, equivalence point is a volume, and it tends to happen sometimes at neutral pHs, sometimes acidic pHs, sometimes basic pHs. It depends on the salt that's made. And that's what helps us select our indicator, right? If we form an acidic salt, then at equivalence point, the solution will be acidic. Does everyone agree? So we'll pick an indicator that changes color over an acidic range. Now, don't worry, I'm overloading us at this point. I'm going to go through all of this soon. It's only because we asked. Any other questions so far? Okay, good. So key things here, I want you to know what the standard solution means. I want you to know what equivalence point means. I want you to know what endpoint means. Okay, and the definition of titration. If you do all those 4 things, I'm happy for us to move on. Okay. Now, you'll see these 2 words being used a lot. Primary standard and secondary standard. Who remembers what a primary standard is? Because this is an experiment you all would have done in year 11. You might have even been assessed on it. So Mahir, any ideas what a primary standard is? It's all right if you haven't learnt it yet.
Yeah, I don't know.
Has anyone learnt primary and secondary standards at school? Mithilesh? Any ideas?
I've like done it myself, but not at school.
Okay, give it a go. What is a primary standard?
Okay, so a primary standard is like a solution of like accurately known concentration. It's formed. Oh wait, no, so that's a standard solution. A primary standard is a substance of that's like really pure. It's like readily obtainable. It doesn't react with like oxygen and stuff. Yeah,
Okay,
it's kind of,
So when we have standard solutions, everyone, you have this term standard solution, right? Let's do it here. The way I think about this is when you have a standard solution, the only thing, the criteria that makes this a standard solution is that it has an accurately known concentration. Now, there are two ways you can accurately determine the concentration of a solution, right? Number one, you make up the solution yourself. You weigh an amount of solute, you dissolve it in a solvent, and you turn that into a solution. When you do that, the solution that you've made is called a primary standard solution. So it is a primary standard. And more specifically, as Mithilesh has alluded to, the primary standard specifically refers to the solute that was made up this way. Okay, so if I get sodium carbonate and I dissolve it in water and I make a sodium carbonate standard solution, the primary standard that was used was sodium carbonate. Does that make sense? Okay, so next to primary standard, I want you to just mention that it is solute accurately weighed and dissolved in solution. That is a primary standard. Now, what is a second way to determine the concentration of a solution? Think about this. You just learned this technique. I was literally defining it a second ago. Alphys?
Titration.
Good, titration, right? So if you ever determine, let's say I give you a solution and I tell you this is sodium hydroxide, determine its concentration. It's already been made up. Does everyone agree? The solution already exists when I've given it to you. You can't already weigh it up, etc. So when you determine the concentration through titration, we call this a secondary standard solution, a secondary standard. Okay, and a secondary standard is one whose concentration was determined through titration. That's it. Determined through titration. Now you might wonder, why can't we just get any solution, or why can't we get any solute, weigh it, dissolve it in water, and ta-da, we've got a concentration, right? It should be that easy. Unfortunately, in chemistry, it isn't. And that's due to the fact that certain chemical compounds, number one, may not even be able to dissolve in water. Right? So if you get 1 gram, you attempt to dissolve it in a liter, half of that may not dissolve. And so straight away, there is a huge inaccuracy in the concentration of that solution. Does everyone agree? Alternatively, if you have a solute that is unstable and reacts with moisture or oxygen in the air to form other unknown compounds, then again, you can't determine the number of moles because the molar mass is changing as the chemical formula changes. Again, you can't find its concentration, right? So as you can see, it's not that easy to create a primary standard solution. There are only very specific compounds in nature that can just be weighed, dissolved, and made into a concentration. Most things in nature will react with the air, will give off fumes and lose mass, will be too small that you have percentage errors in weighing, and so you must go down this pathway, which is titration. Now I have a question to all of you. Why do we care about the concentration of things? Right? You're learning about this fancy method. When I first heard titration, it sounds like a Transformers robot, right? Why should you care about determining concentration of solutions? Let me ask Gerald. Why would it be important?
Like for like medicine, giving like correct dosages to patients.
Yeah,
and like figuring out
good.
concentrations.
Right now, I'm doing my trauma term, and so a lot of patients have been hit by a car, motor vehicle accident, broken ribs. We have to give them opioid medications. Now, if you get the dose of an opioid wrong, you will stop their lungs, you will stop their brain, and they'll die, right? And this is, I'm talking micrograms. If you misdose fentanyl, which is one of the opioids we do, anything over about 300 mics, they will die. 300 mics is a tiny, tiny quantity. So when pharmacists, etc., create medications like this, they need to be very accurate. Any other times where we need to be very conscientious of our concentration of solutions? I'll give you a hint. 60% of your body is composed of this substance, and you consume it every day, and you wouldn't want toxic heavy metals, which occur in trace concentrations in this.
Water.
Yeah, exactly, right? So if you're trying to determine the concentration of lead in water, one way you can do that is titration, right? You accurately determine concentration at trace levels, and you can determine whether it's safe to consume or not, right? So monitoring environmentally in medicine are the main two use cases for titration. Make sense to everyone? Good. Just so you understand why you're learning all of this, because it does fit into the real world. All right, so we've spoken about standard solutions. We've spoken about primary and secondary standards. You can read these steps. I don't care about you memorizing them, but you should generally understand the principles in making a primary standard. So what I'm going to do is I'm just going to hide this from you. I'm going to get someone to tell me. Let's go with, who do we have? Riasan, could you tell me the general steps in producing a primary standard? Now, I don't want you to say, weigh a solute, dissolve it in water, you've got your primary standard. I want you to tell me, what are the specific things I need to be cautious of in the method? For example, when I'm weighing the solid, what do I use to weigh?
Weigh the solid with an electronic balance.
Good. So then once I've dissolved it, how do I just pour it into a volumetric flask? How do I transfer it? That's also very important. Any considerations there? Mithilesh, your turn.
So we've weighed it, right?
Yep, we weighed it. We've dissolved most of it in water. Now, how do I get it into the volumetric flask?
Okay, so first you pour the stuff that's in the beaker into the flask, and then you use like the drip bottle thing to like squirt the rest of the spray it up, and then get all of the remaining residue into the volumetric flask as well, and then you just you fill it up to the point.
Good. I like that you have a good foundation, but there's a few things we're missing here. And that's that we haven't mentioned this piece of equipment here, right? If you're going to transfer a huge diameter vessel into a small diameter vessel, you need to use a funnel for that. Otherwise, you're going to lose solution. So use a glass funnel for transfer. The next thing I want to hear, I know you meant the pasture pipette to bring it up to the specific volume, etc. But you need to also mention that we're going to use a wash bottle. And the goal of the wash bottle is to squirt distilled water that will remove any residual solute that's attached to the walls of the funnel and transfer it into the solution. And the wash bottle should also wash the edges of the speaker and transfer all the washings also into the volumetric flask. Now, the goal of using a wash bottle and using a funnel is to ensure we do not lose any solute in transferring. Does that make sense? So use funnel, use glass funnel, and use wash bottle, and transfer washings is what I want to hear. Transfer washings. Transfer washings. Very good. Does that make sense so far? Good. All right. All right. And you're completely right. We then will continue our wash bottle and bring up our solution until we hit the neck of the volumetric flask. Then a pasture pipette will be used to bring it up to our meniscus line. And what we want to do is this will be our 250 ml graduation mark. And the goal is to have the lower meniscus of the solution at that graduation mark. Okay. Now, the reason I'm telling you all this is not because they're going to ask you this in the exam. They're never going to ask you all this method steps and etc. It's never going to come up in the HSC. Where it can come up is in your practical titration. Your first part of the experiment could be making your own standard solution, and then you can titrate that with a secondary standard. So it is good principle to know how a primary standard was made. Does that make sense? All right, we'll move on in the interest of time. Now, again, Mithilesh mentioned a lot of these points, which is what criteria a primary standard needs to have. Now, I wouldn't advise you to memorize this all word for word. Logically think about it. You know, if you want to get a mass accurately in a volume of water, what properties must it have? And it makes a lot of sense. Why do we need a high purity? So we can actually do our mathematical calculations. Does everyone agree? If I get 2 grams of a solute and I want to find its concentration, well, Gerald, what is the formula for concentration?
Moles over volume.
Good, which means I need to know the moles. And what's the formula for moles? It's mass on molar mass.
Mole.
But if it's not pure, will I ever know its true molar mass? No, right? So then, first of all, it's going to be impossible to do. Now, the next thing, this kind of links it on, is you don't want the chemical to change. This is all linked to high purity. So I would just link this all to pure plus stable. Doesn't react with anything, has an accurate chemical formula. Okay, and again, even this falls under the same principle, right? Non-hygroscopic. Now, this is a new word, so we're going to define this. Hygroscopy, or being hygroscopic, is absorbing water. Okay, so it's absorbing moisture. Now, for your exams, there is one solution you should know has very strong hygroscopic characteristics, and that is sodium hydroxide. It's been asked in past HSC papers, so it's very high yield, you know this. NaOH has a tendency to absorb water from the air. Okay, so as a result, recite, can I ever use NaOH as a primary standard?
No.
No, right? So that's one of the reasons it can never be used. So NaOH is always, concentration is always determined through titration. Very good. Now I have a question for you. I want to see who can think critically and mathematically here. Why should I care for the substance to have a large molecular mass? And I don't want you to just repeat this word for word. I want you to mathematically explain this using maybe an example. Why is having a large molecular mass good? Don't make me pick someone. I want someone to come forward.
Is it just because you have a low degree of error when you use a high molecular mass? E.g., if you were to use a molecular mass which was relatively small, you wouldn't actually be able to measure a mass which was also of like that same degree of measurement. E.g., like if it was a molecular mass of 1, then you would also have to use quite a small molecular mass for you to get an accurate molar measurement. Otherwise, your molar measurement would be off by some amount because you don't have like very precise measuring equipment for measuring mass.
Good. I know you understand that, so I'm happy with that. But I want you to, so I like how you used examples. I'm very happy with that. But I want you to be more mathematical when you break it down. So give the class an example of the error. So let's go with Gerald's examples. Now, what I would say is I want you to imagine that we have, number 1, a solution that has a molar mass. Remember, molecular mass, molar mass, same thing, right? Which is the units slightly differ. Molar mass is grams per mole. Solution 1, let's say solute 1, has a molar mass of 1. Now, what's the unit again, Mahir, for molar mass?
Grams.
Per mole, right? That's what molar mass is. It's what is the mass of 1 mole, molar mass, okay? So grams per mole, right? Now, I want you to imagine that you're weighing this in your beaker. And I want you to imagine that you're off by 1 gram. How many moles are we off by here, Mithilesh?
Oh yeah, we're off by a whole mole.
We're off by an entire mole. That is humongous, because you think about all the calculations you've done. You write 0.294695 moles, right? 1 mole is humongous in chemistry. Now, I want you to imagine solution 2, which has a molar mass. Remember, you need, for thought experiments, go to extremes so you understand this. I want you to imagine another solute that has a molar mass of 1,000 grams per mole. Now, again, if I'm off by 1 gram error, how many moles am I off by, Gerald?
You'd be off by 1/1000.
1/1000th of a mole, right? Negligible difference. Make sense? So to have a large molecular mass specifically reduces percentage errors when weighing a solute. When weighing and also when transferring. Weighing and transferring. The main benefit is it reduces errors when weighing our solute. Does that make sense to everyone? Okay, very good. All right. What about solubility? That logically makes sense. I'm not going to explain that at all. You need to dissolve in a solvent to actually produce a solution. This stuff, forget about. It's not too important. Cheap is because we want to be able to produce this in a wide scale. Now, the next thing you need to know is one example, or two, I would say, this is very easy, of a primary standard. Now, for your exams, the most common primary standard you'll see is this guy here and this guy here. Na2CO3 and NaHCO3 are the most commonly used primary standards in chemistry. So more than likely in your HSC chemistry exams, you'll be given one of these solutions and you'll be titrating NaOH or HCl. Okay, so make sure you remember these are two primary standards. Now on the left-hand side, you can see there are some acid primary standards. I wouldn't even memorize potassium hydrogen phthalate. That's just there for your information. Oxalic acid dihydrate, I don't remember the chemical formula because you haven't done organic chemistry yet. I just want you to understand that it's got two hydrogens. So it is a diprotic acid. So if you ever get this in an exam, they don't give you the chemical formula. Just remember it's a diprotic for now. Okay, so you can write equations with it. Do we have any questions so far? Anything at all? Okay, good stuff. Now, you see this word here, deliquescent, when describing NaOH. This is quite literally means hygroscopic. But NaOH is so hygroscopic that it absorbs water from the air, and it absorbs so much water that it will dissolve in the water that it's absorbed. It forms its own solution, just when you leave it alone. That property is called deliquescence. Okay, so that's what that term means. Good. All right, I think we're going to move on. Now, again, very quickly, Mahe, what's the difference between equivalence point and endpoint? I want you to give it a go. I'll ask one more person.
Okay, I think equivalence point will be like the specific volume which a like the specific volume that which like the reaction would occur, and the endpoint is when all the reactants and products would be finished reacting.
Close, but you technically describe the same thing, right? Volume for reaction to occur and volume to finish for the reaction to finish. Good, but I want you all to realize this, right? This is really important for you learning as well. When you just listen to someone speak, you have a lot of gaps in your knowledge, but you'll never realize that because in your head it all makes sense. The second you speak it into existence, that's when you identify what you don't understand. So what you should do, since you're all muted as well, use the power of mute. You can start talking and explaining it to yourself while I'm teaching it or while I'm going through an example, right? I'm going to ask one more person, Riasa, endpoint versus equivalence point.
Equivalence point is basically the point where the reaction has completely occurred in stoichiometric ratio, and endpoint is when the solution changes color.
Good. I like that definition. Very good, right? So equivalence point is, now the only thing I would change is sometimes we're using terms like, not necessarily you, but students will use terms like when they, or endpoint is when the solution changes color. Now, is that a time? Is that a volume? What is the actual unit for equivalence and endpoint? Remember, it's always volume, okay? So equivalence point is a volume of your titrant required to stoichiometrically react with analyte. That could be one formal definition. Stoichiometrically react with analyte. Endpoint is a volume of titrant that causes a permanent color change. Okay, so the goal here is to make sure these two volumes are the same. We want the volume in which we see the solution permanently changing color. In fact, we can't even say it's the volume of titrant that causes, we can technically say it's when the indicator changes color, because that is what's contributing to it. But just understand both of these are volumes. And the goal is we want the endpoint to occur as close to equivalence point as possible. Does that make sense? Because the goal is to determine this volume of titrant that exactly reacts. And the best way we can do that is hope that exactly when that titrant reacts, we see a color change, aka equivalence point equals endpoint. Okay, very good. All right. Now, again, you can see these explanations in your theory books, but very good. Okay. Now, again, one small thing is, which is with what I was explaining earlier, that the pH at that equivalence point. Remember, at equivalence point, what do we have in it's not the beaker. I'll teach you the equipment very soon, but this equipment piece looks like this. It's what's called a conical flask. And this is where the entire reaction will take place. Now, at equivalence point, there is no more acid or base. So all we have is salt and water, right? So the pH at equivalence point is solely dependent on the pH of the salt. This is why you need to be an expert by now at looking at a salt and telling me, is it going to be an acidic salt or a basic or neutral salt? Because that's going to affect the indicator you choose in your experiment. Okay, very good. Now what I'm going to do is I'm going to actually go all the way here and go straight to the final setup so you understand what's happening. Now we're going to be using the exact same example we used earlier, except now we're going to link it to where it's happening in titration. You hopefully understood the maths of how to determine concentration. Now you're going to determine which solutions are where and what's reacting. So again, what was the reaction we used as our example, Alphys?
Pardon?
What was the example we used for our titration, for our example at the very beginning? Remember the chemical reaction?
Was it HC?
plus HCl, yeah.
Yeah.
That's a very easy example. NaOH plus HCl. Okay. Now again, we said, I believe we said our NaOH was that of the concentration we knew, and our HCl we didn't know the concentration of. So we're going to keep it that way for our understanding. Okay. So again, Maher, who's the analyte? Who's the titrant?
The analyte would be the HCl and the titrate would be NaOH.
Good, right? We're analyzing the analyte, so we call it such, and the NaOH is your titrant. Very easy, right? Good. Now, I want you to remember this. Where did we say the reaction was going to be occurring in? What instrument or what piece of glassware? I just mentioned it. Mithilesh?
The conical flask.
Yeah, conical flask. So everything is going to be occurring in the conical flask. Okay. Now, typically what happens, everyone, and remember there are exceptions. You may see the exact opposite occur in some calculation questions. So it's just a general rule of thumb. We like to have our analyte already sitting in our conical flask. Okay, so our analyte is typically sitting neat and cozy in the conical flask. And does anyone remember what volume I told you we would always have of our analyte that we'd be analyzing?
25.
25 ml, very good. So we'll be using glassware, and we'll talk about that soon, to accurately determine 25 ml. In fact, it'll be 25.00 ml of our analyte solution, which will be sitting here. Okay, and in this case, the analyte is HCl. So we're just going to write this. We don't know its concentration. Now, this long piece of glassware that you see, this piece of glassware, this is what's called your burette. So we're going to write burette. Okay. Now, the burette is something you may have never ever seen before, because this is what we call a volumetric piece of glassware. And my tip to you is, you know it's volumetric when it ends in et. Because there's going to be another piece of glassware I'm going to teach you very soon that ends in et, and you're going to tell me it's a volumetric piece of glassware. Now, what does it mean to be a volumetric glassware? Gerald, any guesses? Break down that word for me.
It can contain a specific volume, like specific known volume.
Very good, right? It can accurately measure volumes. Now, the beauty of the burette is that it allows you to deliver variable volumes. The burette can choose to deliver 10 ml, 15 ml, 20 ml. And the way this works is we have an initial reading of solution. So this would be where the solution was initially drawn up to. And there'll be markings on this burette like this. Okay. And does everyone see this little turning wheel here? It's what's called a stopcock. That's what we call that turning wheel. Now, when that wheel faces parallel with the length of the tube, like this, the solution will freely flow down like a waterfall. You don't want it to flow like a waterfall ever in titration. You want to be anal, so you want to always, that's why it's put at this angle, where it starts to flow at what we call a dropwise rate. Okay, when you put the stopcock in this orientation, perpendicular to the length of the burette, it'll be completely turned off, no solution flows. So does everyone agree, by opening and closing the burette, you can choose to deliver variable volumes of solution? Right? Now what's going to happen is when you start the titration, remember the initial volume would have been all the way up until our initial reading, this one here. Okay, and you would record this to be 0.00. Wait a minute, that's a bit weird. Why would the measurement at the very top be 0.00? What does that tell you about the incremental measurements as we go down? Everyone?
Negative.
The numbers
Negative?
get larger. It never goes to negative, but it gets larger, right? So the burette is actually, the measurements are placed that way such that the bottommost reading will say 50 ml, because 50 ml is the typical size of the burette that you will be using. It'll say 50.0. It'll say 0.00 ml. Okay. Now, what you're all going to be doing is you're going to be turning that stopcock and you're going to be delivering our solution in the burette. Now, everyone, if our analyte's in the conical flask, who's sitting in the burette? Alphys, who's sitting in the burette?
Would it be the NaOH?
Good, which is called the
titrant.
Good. Again, remember I told you, this is a rule of thumb. Sometimes this is completely swapped. Sometimes the analyte will be in the burette, and they like to do that to just trick you. But remember, generally your analyte's in the conical flask. Generally, your titrant is in the burette. We'll talk about what it means when we swap them around, how it's going to affect you as a student. Not much really, but coming back to this, titrant in the burette, analyte, conical flask. Now, when you open the stopcock, you'll slowly be delivering this titrant. Now, remember, you have indicator in this conical flask, and you would have chosen the indicator based on what aspect of the titration. What is the number one deciding feature which you'll be using to determine what indicator we use in titration? So, Gerald, what is the number one thing you want to know about this reaction, which will determine what type of indicator you use?
The resulting salt.
Good, right? So the only thing Gerald cares about is what is the salt. If the salt is acidic, he's going to choose an acidic indicator. The salt is basic, he's going to choose an indicator that changes color over a basic range. Does that make sense to all of us? Okay, so good. Now, what's going to happen is when we start delivering our titrant in the burette, we start to see color change. And the reason that happens is because there's going to be a concentrated area of our reagents reacting and neutralizing. So you'll see flashes of color change. Now, endpoint is not just when you see a color change, it's when you see a permanent color change. So what you'll be doing is you'll be swirling this conical flask to ensure there's an even distribution of our reagents. And the second you see a permanent, faint color change, you'll stop your titration. Now, let's say you stop the titration and we reach this mark, 50 ml. What is my end point, Mithilesh? Started at 0, we ended at 50. What is the end point?
50.
Good, right? Remember, it's a volume, so that's what I'm asking you. And it's the volume which was required of the titrant to completely change color for the solution. And do we agree? It was at 50 ml for our example. Now, we hope the indicator changed color exactly when both reagents reacted. We don't know for sure, but we hope so. We would have chosen an indicator that changed color exactly at pH 7. And so we hope equivalence point is as close to 50 as possible. Now I want you to imagine that we have our concentration of NaOH, which is 0.1. And I want you to imagine that the volume we just calculated was 50 ml. I want you to determine the concentration of analyte. I'm going to tell you anything. I want you all to give me an answer. So I want you to raise your hand once you've got your answer. It should be quite fast. Good, very quick. All right. So in fact, Riyasat's got 2 hands up, very eager. What's the answer, Riyasat? How do you determine this?
0. Use you find N of NaOH.
Good.
Yeah, so that's CV, so that's 0.1 times 50 times 10 to the minus 3, which I got as 50 times 10. Yeah, 50 times 10 to the minus 4. And that's equal to the number of moles of HCl.
Good.
And then you can find the concentration of HCl is equal to N on V, which is 50 times 10 to the minus 4 over 25 times 10 to the minus 3, which is 0.2 molar.
Easy, right? Good job. How many sig figs? In this case, it would clearly be
1.
Good. How easy was that? Titration is easy. The calculation is very easy, right? The reason it's easy, everyone, is because there's no excess limiting reagents. It's just straight stoichiometric calculations. I want you to remember this. The hard part is the method. Doing this method to a T is the hard part. And this requires not just studying paper and pen, but when you go through this at school, I want you in that practice lesson, when the teacher shows you how to do the practice titration, while your friends are relaxing and taking it easy, you should be focusing 100%. Because I wish I did that when I was doing my experiment in retrospect, because the technique is something that a lot of book smart students don't necessarily do well, and it hurts them in their internal assessment tasks. I don't want that to be you guys. Okay, so make sure when you do it at school, you take pictures, right? When you do it at school in your workspace, take pictures of every step. You know, record your friend doing it, or I don't think you can record your teacher, but generally try to get as much info and data you can so you can add it into your notes. Okay. I would also advise you watch YouTube videos on this as well, because no matter how I teach it to you, you won't understand it unless you see it in person. And I don't want to just pop up a YouTube video because then I'm not doing any teaching. So do that in your own time. All right. Any questions so far with the general method of titration?
I had a question about the calculation.
Yeah.
We can't use C1V1 is equal to C2V2, right?
Okay. In this question, it would have worked out. But I want you to tell me, Mithilesh, if I put a 2 here and I put a 3 here, would that work out? C1V1 equals C2V2? No. The only reason that works, think about this. What is C1V1? That's just N1. What is C2V2? It's N2. So only when N1 equals N2 can you use C1V1 equals C2V2, right? So that assumes there is a 1-to-1 ratio between both reagents. In this case, there is, but in all titrations, there may not be. I want you to never do that though, because I want you to always think C1V1 equals C2V2 is a dilution. This is a chemical reaction that is happening, which is completely different. Does that make sense? So if your teacher has taught it to you that way, that is not right. It sometimes works, but you always just follow this method. C1V1, C2V2 is dilution only, full stop. Good. All right, I've got pictures as well to show you. Here you can see the experimenter swirling the conical flask. This is actual technique. Your right hand should always be on the conical flask and your left hand should be turning the stopcock. I find that weird because you don't, I personally think you'd want your right hand, which has high dexterity, to be turning the stopcock, which is very sensitive to rotation, right? But this is the technique you should be doing if you do titration at the school competitions, and they look for this a lot. So I guess just learn how to be ambidextrous, you'll be fine. All right, we're not going to go through that calculation stuff. We just did that. So how about we start doing some of these questions? We'll skip one, very easy. Easy. Here you go. Okay. Now, I don't know if I should go straight to that for you. Yeah, okay, sure. Now, with this question, everyone, actually, first I'll get you to do an easy one, just so you get comfortable. So I want you to do question 1C for me. Fast as you can. When you get an answer, let me know. After this question, I'll give you all a 5-minute break. Good job. Mithlesh, could you actually don't tell me your answer? Wait for someone else to get their answer.
Wait, are we doing just 1C?
Yes, just 1C. Yeah. This usually in the HSC 1C you will require data calculated from BNA. So take that into account. This question is not the case. Good. I think everyone's got it now. So Mahir, what's your answer?
0.3.
Okay. Mithlesh, yours?
Yeah, same.
Good. 2 out of 5. So I hope everyone got the same answer. So we will move on. Good. So as you can see, direct titration questions are very easy. Now, I'll be frank, you'll never get a question this easy in your exams. Never. Okay, this is just so to ease you into titration. Typically, your exam questions start off to look like this, right? Now, I want you to interpret what's actually happened here. When we see the word titer, what does that remind you of? What word is that reminding you of other than titration? Because of course, that's what the experiment is.
Titrant.
Titrant, right? So the titer is the volume of titrant required. Now, I want you all to look at these titer values and tell me, do they all seem concordant or similar to one another, or is there an odd one out? What does it look like to you?
One's a bit off.
Yeah, right. Now, my tip for all of you is when you are doing titers, especially when you're doing a school one, your first titer is always what is called a rough titer. And the reason it's called that, everyone, is because your first titer, you will always overshoot endpoint because of human error. You will see a color change, your hand will keep turning because your reaction time is too slow, and you will always overshoot by 1, 2, 3 ml. Does that make sense? So when you do the titration a second time, yes, you repeat the titration multiple times. The second, third, fourth time you do it, what you'll do is when you see 24.7, you need to subtract 5. Jared, what's that equal to?
19.7.
Good. So now Gerald knows the second he starts reaching 19.7, so he'll be opening the solution, letting it flow into the conical flask until he gets to about 19.7. You're not going to fully open it, but you allow it to go a little bit faster. At 19.7, Gerald knows he needs to start going at a drop-wise rate. Okay, so now what he'll be doing is every single drop he adds, he'll be stirring the solution. So with his right hand, he'll be turning it, waiting for any permanent color change. If he doesn't see it, he'll add another drop, repeat. Another drop, repeat, 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 repeat. Does that make sense? Until he gets to a permanent color change. And so when he does it, he'll get this. And the goal for Gerald and all of you doing your titration experiment is you want to have 3 titers. This is the hardest part of titration, to get 3 titers that are within 0.2 ml of one another. Those are what we call concordant titers. Some textbooks have 0.3. 0.2 is typically a gold standard. Now, what do we see here, everyone? Are the titers within 0.2?
Yeah.
Yeah, so if they're outside of 0.3, you would discard them. So if this was 21.8, you would take that one out as well. Does that make sense? And you'd use the 2 and the 3. So they need to be within 0.3 or ideally within 0.2 of one another. Okay, so what do you think we do now? It's basic scientific principle. You remove the outlier. What do you do with the remaining results?
Average.
Good. So I want someone to tell me, what is the average titer?
21.45.
Good. All right. So we'll leave that there for now. So I just wanted to show you how to interpret these titration tables. Very easy. Remember, discard the first titer, even if it's concordant. Unless you've been only given 3 titers, discard the first one. Okay? And then with the remaining 3, you would average it. Usually in your exams, they'll always give you 3 concordant titers. Okay? Now, before we do this question, I want you all to take a 5-minute break because you've hit the hour mark. And we will recap at 7:17. Okay? Stand up, get some water, get a snack, and then come sit back down at 7:17. Okay? All right. See you guys in 5. All right, you can turn your cameras on when you get back. Okay, so this is also quite an easy question. It's a titration with one extra step. So again, I'm not going to say anything. When you guys are ready, I want you to start working through this question. So I've helped you out on how to interpret this table. So hopefully you took notes. Always discard the rough titer. Find 3 concordant titers and average them. When I say concordant, it's within 0.2 ml. Okay? Right. So go for it. The one thing I want to see, I don't care about your answer, is whether you followed the steps that I told you for calculation. The same thing applies here. If you start deviating from it, then you'll start making mistakes. Okay, so I'll give you all a minute or so. Was anyone invested in cryptocurrency here? No one? Well, interestingly, I've been investing. I mainly invest in the share market. But one of my friends in medical school, he's been investing for 6 months now, and he'd actually accumulated $2 million in return in the 6 months. And because of the recent crash, it's gone down to 400,000. And so now I feel extremely, extremely poor because I've been investing for 2 years and haven't got even maybe 1% of that, which is insane. But it's quite interesting to see. At least I want you all to at least observe the changes in the world that are going on around you, because especially with a lot of old conservative people, a lot of parents as well, they aren't open to researching or even investigating how all of this works, and whether it's speculation or whether there's any underlying promise. So I think being self-directed is a really big skill that all of you, while you're young, should be doing. Learning how to code would be really good. So those are skills that I wish, if I was you in your shoes, I would be doing on the side when you have time. Okay, let's get started. So Maya, start off with you. What's the first step?
So I wrote down the equation.
Yep, what is the equation?
C6H8O7 plus NaOH.
How did you know it was C6H8O7?
I searched it up.
Oh, okay. You didn't have to search it up because you can't do that in the exams. It's triperiodic, right? So I just wanted you to write H3A or H3X. Yeah?
Oh,
I was very surprised that you knew it because it's not required knowledge in the new syllabus anymore. You're right, it is C6H8O7. All right, so it's H3X is going to combine with what?
NaOH.
And what do we form?
H2O.
Yep.
And NaX.
Are you sure it's NaX? I want you to think about this. Where did the 3 come from?
The X.
Good. So when you combine Na, which has a +1, and X, which has a 3-, would it be NaX or would it be Na3X?
3X.
Good, right? So make sure you don't make silly mistakes there, because it's going to affect your stoichiometric ratio, right?
Yeah.
So Mithlesh, bounce this for me.
Yeah, so there's a 3 in front of the sodium hydroxide and a 3 in front of the H2O.
Good. All right. So should also write our states very quickly. All right, Judd, what do I do now?
Now you would find the moles of NaOH.
Wait a minute. We're jumping it. What's the second step in calculation questions?
Write down all your information.
Good. What
All
information
values.
do we have?
So you know that there's 25 milliliters of the triprotic acid.
Give it to me. It's V of what is 25?
Okay, so V of or the citric acid is equal to 25 mils.
Good.
You don't know the concentration of the citric acid.
Good.
And the concentration, the volume of the sodium hydroxide solution is 100 mil.
Okay.
And the concentration of the sodium hydroxide solution is 0.1 molar.
Okay. Okay. What's the next step, Alphys?
Oh, you'd use the C equals N over V for the NaOH.
Before that, again, I'm being very strict with this because even if you start deviating in easy questions like this, you will get pummeled in hard questions, right? So follow the steps that we did in our previous lesson. So after you write data, what do we do?
We're trying to frame the question.
Good, right? Even before that, there's something more visually that we can do. What is that?
Diagram.
Yeah, right. So here, do you see there's dilution? So this is where a diagram will help you, right? So a 25 ml volume of citric acid, H3X, has been diluted to 100 ml of H3X. So what does that straight away tell you? There must be a C1 and there must be a C2. Does everyone agree? Because we got a V2 and a V1. So now this is actually going to help you with your data, because what V is this? Is that V1 or V2?
That's V1.
Good. And what's actually participating in the titration? Is this tiny test tube participating in the titration, or is it the actual beaker that I've drawn up that actually gets reacted with that NaOH?
The beaker.
Good, right?
Prithvi, does that actually matter though? Because in the end, it's like the same like moles.
I'm not sure. So mathematically, it might not matter, but it's good principle to do this, and I'll tell you why. And I'll tell you the reason here, because you're going to find out very shortly. Because now V2 is 100 ml. But wait a minute, whenever you're doing a titration, you should also draw up the actual equipment for titration. So even though this V2, which is 100 ml, is the one being titrated, do we titrate 100 ml or do we titrate a different volume? And to answer that question, I want you to tell me, who's sitting in the burette, who's sitting in the conical flask right now for this question?
The titrant would be sitting in the burette.
Good. Okay. And who's the titrant? That's what I want to know. Is it NaOH? Is it H3X?
NaOH.
Yeah, good. I want you to actually tell me, Mithilesh, what's the definition of a burette?
A burette. So it's like a variable provider of volume.
Good. Volumetric equipment that delivers variable volumes of solution. Variable volumes is the key word. They actually test this in HSC MCQs, so never forget that, okay? So we know that our NaOH is here. So who's sitting in the conical flask, everyone?
The citric acid.
H3X. And what volume can the conical flask hold? Not 100 ml. What volume can a conical flask hold?
50.
Not 50. The burette holds 50 in total. Well, how much volume does a conical flask hold?
25.
25 is the answer, right? This is why diagrams are so important. So out of that 100 ml, to continue our diagram, this all goes back here. 25 ml of that 100 ml is taken for the titration. Okay, now I want you all to tell me what concentration of H3X would we have? Would we have C2? Would we have C1? Or would there be a C3 because there's been another dilution? What's the C value that we'll be finding from titration here?
C2.
C2. Does everyone agree? There hasn't been a dilution. When you take 25 ml of 100 ml solution, you take less moles because the volume is tinier, but the concentration is always constant. So when you do your titration calculations, everyone, you'll be finding C2, and then you'll be working backwards to find C1. Does that make sense? Okay, the question is asking you the concentration. This is the next step, which I kind of jumped and didn't explain to you, is they're asking for concentration of citric acid. Frame the question. The question is C1 of H3X equals to question mark. Does that make sense? That is the ultimate goal. So how do we get to C1? We find C2. Let's start working backwards. We find C2 through our simple titration. We then have the C2 here, so we can work backwards through C1 V1 equals C2 V2 to find C1. Everyone with me? So let's start working through this together. So now we know this is our V. The V actually doesn't change to 100. It's still 25 because that's all the conical flask can take. So N of NaOH, which is what Alphys has mentioned earlier, equal to CV. What does that equal to, Alphys? N of NaOH.
It's 0.01.
Is that what everyone else got?
N of what?
NaOH.
No, but you got 2.143 times 10 to the minus 3.
Are you sure? Because all we're doing is we're getting the 100 and we're timesing it by 0.1. Why are we getting a different value for N of NaOH?
Yeah, I got 0.1.
Okay, wait, no, I did something wrong. No.
Okay, so everyone, what's our final answer? Is it 0.01?
Well, I'm confused. Where are we getting the 100 from?
Wait, didn't you say you were meant to find the average titer value? And
Yes,
then
that is right. Sorry, I was asking you all for data. I think someone gave me 100, but the answer is yes. The average titer is 21.45. The average titer is this value. And what is the average titer? It's titers of sodium hydroxide, which is in our burette. So yeah, it should be 21.45 times 10 to the power negative 3. Completely right. So a number of moles of NaOH is equal to CV. And now what's our new value?
2.143 times 10 to the minus 3.
Good, thank you. Let's store that as A, right? So rheostat, what's the next step? I found my number of moles of NaOH. What can I do now?
You can find the number of moles of H3X.
Good, and what is that equal to?
So that's that's A on 3, which
Good.
is yeah.
So I would say itself over the other. So the number in front of itself, which is H3X, is 1. The number in front of the other compound, which is NaOH, is 3. So 1 on 3 times the number of moles of the other, which is A. That's equal to A on 3. Very good. So now we've got the we'll store that as B. A on 3 is B. Okay. So we've got the number of moles of H3X. We have the volume of H3X. What can I find now, Gerald?
You can find the concentration of H3X.
Which concentration? C1 or C2?
C2.
Good. So your C equals N on V equals B divided by 25 times 10 to the power negative 3. What do we get?
2.8573 times 10 to the minus 2.
73 times 10 to the power of minus 2. Good. So that's C2. Now remember again, we want to find C1. So store that as C. So now we can say C1 V1 equals C2 V2. What is C1? C1 is equal to C2 V2 divided by V1, which is B That's C2, because that's what we just found. We stored it as B. Sorry, we stored it as C. So, apologies. So again here, let me just highlight that for you. C2, we got this value here. We stored it as C. So I'm going to be using a C here. Okay. My question to you is, what volume do I use for V2? Do I use the 25 ml that was used in the conical flask in the titration, or do I use the 100 ml that's in that big beaker?
The 100.
Yeah, good. Do you see now why diagrams are helpful? Since there's so many different volumes, when you see a diagram, you see, well, where did the dilution happen? I'm doing a dilution calculation. The dilution happened from this step to this step. So of course, I'm only going to be using volumes in those steps. And in this case, V2, we've clearly denoted it as 100. So I don't even have to think. So V2 is 100. As you can see, a lot of areas students can make silly mistakes in can be omitted if you draw a diagram. And I'd advise you from now on to always do a diagram if it's a bit of a tricky titration question. If it's easy like the ones you did above, which you'll never ever get, you don't need to. But most of your titration questions, you'll have to do a diagram one way or another. Okay, what is V1? Well, we've denoted it here already. V1 is equal to 25. So V1 is 25 times 10 to the power negative 3. And what's our final answer?
1.143 times 10 to the minus 1 molar.
Good. 1.143 times 10 to the power minus 1. Okay. Is it minus 1?
Yeah, minus 1.
All right, so isn't that just 0.1143? You can write it a little bit nicer. And how many sig figs are we rounding it off to?
1.
Good. Very good. It's 0.1 and 100. Yeah. Yep, very good. So 0.1 moles per liter, 1 sig fig. You'd write number of moles of H3X rounds off to that. Good, and that would be a perfect answer. Now, did that make sense to everyone so far, what we did here? Right? Do you see why following the steps that I gave you are so important, especially when you do questions like this? Now, did anyone already see all of those small nitty-gritty things that we accounted for? And did anyone get the answer before I actually solved it here? Okay, good. So what I want you all to do is get a red pen, and whatever mistake you were about to make before I intervened and went through the steps, I want you to write down so you don't make that mistake again. So whatever it be, whether it be draw diagrams, or C1V1 equals C2V2, or whether it be 25 ml always in conical flask. Write your mistake down, because the main thing in chemistry is you don't make the same mistake again. This is so important, guys, because last year, HSC Chemistry, every single state ranker got 100. So if you want a state rank in chemistry, I guess you have to be aiming for a perfect mark. It's weird. That wasn't the case. In my year, I got 97 or 8, don't remember, and that was 5th in the state for chem. So I don't know if the exams have gotten easier or kids have just gotten smarter. I don't think it's the latter, because, yeah, but we'll see. All right, what we'll do now is we'll go through this question here. I'm not going to say anything, but I want you to tell me, what is percentage V/V? What does that mean to you? Percentage V/V.
Percentage volume over total volume.
Okay, and what does that mean mathematically? So if I asked you, Gerald, percentage V/V, how do you understand that? What does that mean to you in simple terms?
It's like the percentage of a substance in a compound.
Okay, percentage of a substance in a compound. All right, then anyone want to clarify further? Otherwise, I'm going to let you all go with Gerald's definition to solve this question. I'll keep the end here. This is our answer, 0.1. Riasat, any ideas? Percentage V/V, what does that mean to you? This is very high yield. They definitely ask it in trials because they know students forgot this from year 11. And this is one of those small things from year 11 which carries on straight to year 12 and is mandatory known knowledge.
Well, I see percentage V/V as how much, well, like essentially the percentage of like volume of citric acid, or like the solid in the solvent, I guess. Like the volume of the solid over the volume of the solvent. Yeah.
Okay. All right. Sure. Okay. For this question, just based on the data that's been given, I need to give you a bit more information, which is going to be that the chemical formula of citric acid is C6H8O7, and I'm going to change this to W/V because you technically can't find V/V, and you'll find out why soon. But okay, sure. Since you've given me two definitions, I'm going to leave you to it. Calculate and tell me, how do I find percentage W/V? So V/V was volume/volume. What is W/V? You guys have a minute to do this before I ask for answers. So go as fast as you can. If you want, I can scroll out so you can see the entire question. Sorry, here it should have been a C of H3X. C. You're finding concentration, not number of moles. All right, we've got one answer. So Gerald, what did you do?
So I first calculated the mass of citric acid, which was present in orange juice. So to find mass, used moles. So to find moles, you would have to do 0.1, which is the concentration times volume.
Okay, good. C
And
saying is CV, good.
yeah, and then once you do that, you then times it by the molar mass of citric acid.
What did you get as your number of moles?
Oh, number of moles. Wait. I think I had an error with mine. Just wait.
Anyone got number of moles?
I did like a different thing. So I just used the concentration 0.1 and then just made the whole thing 1 liter.
You made the whole thing 1 liter. How did you make the whole thing 1 liter?
Because it's isn't it a percentage? So like if you change one, the other one changes as well.
Okay, so if you make it to 1 liter, then what happens to the concentration?
It stays as 0.1.
Okay, then what happens to number of moles?
It's 0.1.
Okay, right. Okay, so look at your way. Yeah, that mathematically makes sense, but we'll see what happens. So assume 1 liter. I would, just to be safe, have one method you'll always stick to. So the one thing I'm not going to do is go through 2 different methods simultaneously, because that's going to confuse us. So I get where you're going from, Mithilesh, so I want you to either stick to that way or follow this way. We'll see if your final answer is correct. So who's got maths for me?
Like the answer.
Yeah. What is sorry, what is n?
So for n, well, I didn't really calculate. I just put into one big equation for mass.
To store it as A. So mass is equal to number of moles times molar mass, which is equal to A times the molar mass, which is C6H8O7. What do we get as our mass?
0.480131.
Okay,
Grams.
so that is B. Okay, so I want you to remember this. Percentage W/V or V/V. So V/V just means ml per ml. But since it's a percentage, we always divide by 100, right? Because that's what you do to convert a fraction to a percent. Usually times it by 100. I know, so this is actually technically not intuitive, but percentage V/V is ml per 100 ml. Okay, so that is the standard denotion. Same way, percentage W/W is equal to grams per gram. That's what W is. But since it's a percentage, we add 100 in our denominator. Okay, I know what you're thinking. Usually fraction to a percentage of times by 100, but in this case, it's divided. Okay, so that's why students do often stuff up these questions. So when I asked you for W/V, I'm asking for, so percentage W/V, what is that? Grams per 100
milliliters.
Perfect, right? So we're getting the hang of things now. So very good. So you found grams, and how much ml do we have? This is in 100 ml, so it's already been done for us. Do we agree? So right, therefore, percentage W/V is equal to, so it's B grams. This is the amount of grams that was in 100 ml of citric acid, so we just do B. Grams on 100 ml. So the answer is just B. Does that make sense to everyone? Because this entire solution was already, where is it? Oh, sorry, it was 25 ml. 25 ml was the initial volume of the orange juice. So I apologize. It was diluted to 100. So we have B grams in 25 ml. Is everyone with me? Right? Going back to the previous question, it was diluted to 100. I accidentally misinterpreted that as 100 being the original volume. Going back up, we see that 25 ml is the original volume. So B grams, which is what C1 or the original concentration was, that is in 25 ml. So what I would write here is I would write, therefore, there's B grams in 25 ml. How many grams would there be in 100 ml? What would we do? Times by 4, right? So you can say, therefore, concentration or percentage W/V of H3X is equal to 4B grams per 100 ml. What is that equal to, everyone? What's 4 times B?
1.6124.
Okay, so the way you denote percentage weight per volume is you just write percent W/V. That's it. And it's a concentration, because remember, it's a solute over solvent. So that's why it's still a concentration measurement. How many sig figs? Again, 1 sig fig from the previous question. So 2% W/V, 1 SF. Does that make sense to us? The key thing you have to remember, the learning point for this question was just this. If you knew this, the question would be easy. Right?
Prithvi, I think there's a bit of for the number of moles of H3X. I think it was. We multiplied it by 0.1 liters, 100 milliliters. Even though the concentration is like the
Yes,
concentration in the orange.
agreed.
So
Yeah, I agree
all
with
our
you.
calculations have been wrong. Like after that.
Yeah, you're completely right. I messed up there. I assumed that the original volume was 100. The original volume was 25. Agreed. So we use C1, so we should be using V1. So 25 should be the answer the whole time. Okay, so very good pickup. Good. I agree with you. What you can do is very quickly just look at how that will change your answer, right? So this is answer should be fourth of that.
I'm pretty sure the answer is the same because I already did that in my calculations.
Oh, good pickup.
Yeah.
Good job. Very good. This is why you should have the whole question in front of you. So I zoomed in, so I apologize, but you're 100% right. It's good. You're all picking up errors as well, which tells me that you really understand what's happening. Do we have any other questions at all for how to calculate percentage weight per volume, volume per volume? This comes up a ton in your exams. No? All right. Very good. In the last 10 minutes or so, what we're going to do is we're going to start going through some tougher questions. Yeah. Some quite tough questions. Maybe some trial questions too. Right, we might start with HSC Chemistry. I don't even know which paper this is from. Should have been labeled, but here you go. I want you to do both these questions. When you got an answer, raise your hand. The next 10 minutes is solely going to be trial question after trial question. Just call this page 71 HSC Chemistry. Okay, 2 students have got their answers, so we'll start going through this. So let's go with Mahe. First question, what's your answer and why?
I got D.
Okay. Risa, first question, what'd you get your answer as?
I got C.
Okay. Alphys, you want to add some more contention here? Is it an A or B?
Yeah, I got A.
I feel like we're doing this for comedy. Gerald, B?
No, I got C.
Okay, C. Mithilesh?
I got A.
Okay. All right, so we're spread out. It's like it's not even a bell curve here. It's just everyone's picking different options, which is good, which means all of you have a lot to learn, and one person has got this correct, I guess. Again, this comes down to the maths, right? Now, what did I tell you all about neutralization reactions? All neutralization reactions go to
Completion.
completion. Very good. So Maya's brain is collecting what he learned a couple of weeks back and coming back to him via auto memory, right? So all neutralization goes to completion, right? So let's just take that into account. Let's do this question here. We've got NaOH, and he's titrating a weak monoprotic acid and a strong monoprotic acid. Now, everyone, let's write the equations, right? NaOH, he's titrating a weak, we'll call this weak monoprotic acid, and he's titrating a strong monoprotic acid. Now, what did we say? All neutralizations go to completion, right? Unless it's water. Of course, only in water do weak acids partially ionize, all of that, which we've spoken about. So what products do we form, everyone? NaA and H2O for both of them, right? So I'm not going to write this twice. Now let's write down our data. We're using the same concentration of NaOH. We're titrating the same volume of HA. We're titrating the same concentration of HA. Now, what is this question asking? Volume of base required. So we're trying to find this V. That's what we're trying to find, right? Now I have a question to all of you. These two C and V values are the same. These two C and V values are the same. What does that mean for the N values for HA for both of these acids?
Same.
The same. So what does that tell you then about the number of moles of NaOH required? It's a 1-to-1 ratio. It's going to be the same in scenario 1 and scenario 2. So then what does that mean for the volume? Well, C equals N on V. V equals N on C. Right? So V equals, nope, apologies. That is completely wrong. What am I doing? We're trying to find our volume. So we're at V equals, yes, that's right. V equals N on C. Now, what have we been given? We've been given the same concentration, and we know the number of moles of NaOH is going to be the same. So this N will be the same for scenario 1 and 2. The concentration of NaOH will be the same for scenario 1 and 2. So what does that mean for the V of NaOH? Everyone?
Same.
The same. Does everyone agree? Does everyone see what we just did here? Mathematically, we've shown that the volume of base required will be the exact same as weak acid and a strong acid because all neutralization go to completion. So I hope this clarified a lot to all of you. Mahe, do you see in the maths, we didn't even use capital M molar mass. So that shouldn't have any effect at all. Molar mass only starts mattering when you start trying to calculate the mass of things, right? If the question was the mass of the acid or XYZ, then of course you have to use molar mass. It's going to affect your variables. And Alphys and Riasat, did you see, and Gerald, did you see how we applied the principle, which is we used single directional arrows. I think maybe you thought there'd be double directional arrows. Is that what we were thinking?
Got A.
Yeah, I think Alpha's got it correct. But
Oh, good.
me and Risa, I'm guessing it was just that like weak acids won't have as much of the hydronium ion in solution. So if it was to get
See, you'd think that, right? You'd think they wouldn't have as much ion, but the second they react with a strong base, what is that going to do? It's going to disturb the equilibrium,
shift
shift
equilibrium.
it. Yeah. So I see where you're coming from, and sorry, Alphys, you did get it correct. My bad. So good job, Alphys, and who was the other one? Mithilesh, I think. But good job. So that was your answer for the first question. Second question. Let's quickly do this. And this is so important. By next lesson, you definitely should do all of these trial questions here. Every single one. Even checkpoint F if you can. I would go as far as saying do as many as you can, up until checkpoint G, if you can. You have 2 weeks to do it, but ideally, if you can do it all in a week, you will not have to worry about titration. Actually, I would say split it into 2 study sessions. And that should be in the same week because you should be revising chemistry every once in 2-3 days. So yeah, by next week you should be doing that. And unless you have a chemistry assessment, don't worry about what your teachers teaching you in your class sheets. Do the trial questions. They'll help you way more. Okay. All right, let's go back to where was our question? All right, we'll quickly do the second one. pH at equivalence point for both of these titrations. Now, who's got an answer already for this one?
I got B.
Okay. Anyone else got an answer already?
Yeah, I got B as well.
I got
Okay.
B as
Very good. So let's just very quickly do it since you all know the answer, I guess. NaOH. We're going to form NaA for both of them and NaA for the second one as well, HA plus NaOH. I'm not even going to draw water because it's useless. But Alphys, if this is a strong acid, right? This HA is a strong acid. So what does it tell you about the A, which is the conjugate base?
Maybe very weak.
Very weak or neutral. And we know the sodium is always neutral. So for the strong acid, strong base titration, the pH will be 7, aka neutral, at a equivalence point, right? But here we have a weak acid. What's the conjugate of a weak, Mithilesh?
Weak.
Yeah, so conjugate of a weak acid is a weak base. And this is a neutral ion. Sodium is a neutral ion, weak base, right? So that means pH is going to be greater than 7. So let's see which one will be the option. One of the solutions will be neutral, the other will have pH higher than 7. Perfect, B. Cancel out the others. Neutral and lower than 7, that's wrong. Higher than 7 and lower than 7, that's wrong. We said it's going to be 7 and greater than 7. The answer is B. Very good. Good job. Did anyone have any last questions on titration before we end today's class?
Yeah. Is back titrations like a whole lot different from normal titrations?
Yeah, they are. The approach is different, and the reason is very quickly summing it up, and it's not going to be justice to sum back titration in 10 seconds. But in back titration, you usually do this when the direct titration is too volatile, or it doesn't go to completion, or you can't use an appropriate indicator because the pH range is really narrow at equivalence point, right? Things like that. Or if it's a toxic reaction, something like that. So in back titration, if I'm trying to determine the concentration of this solution, I'm drawing it as a puddle. Imagine a puddle on the ground, right? If I do a direct titration, everyone, what does this involve? It involves exactly reacting this black puddle with another solution, which could be an acid, which is our blue puddle. And exactly when they react, that's equivalence point. Does everyone agree? Now, for a back titration, what we do, so imagine that same puddle, we add an excess of a reagent. So imagine the black puddle is your acid. We're going to be adding base. We're going to keep on adding base until we add an excess of base. So this is going to be the excess of base. Then what we do is we titrate that excess of solution like this. And we can use maths to determine the concentration of this black solution here. That is a back titration. So a direct titration is a single reaction. A back titration is actually two reactions. An excess limiting reagent reaction, which is the first step, and the second step is a titration. Now, again, this is going to take a whole lesson to teach. So if you didn't understand that, don't worry, no stress. We'll touch upon it next lesson. Has anyone learned it at school already? Okay, well, good. It's good that you're doing your own research. Now, are you all finding school easy? When you're going to class, you're learning the content, are you ahead of it? Do you understand it? Does it make sense?
Yeah, I think everyone thinks, yeah, we're pretty far ahead, I think, because we're still doing like pH and POH at school right now.
Good. And are the calculations you're doing it at school? Make sure, again, it's another thing, just because you feel ahead, this is a selective student mistake. I see so many students doing this, is they get confident and they get lax. Now, when I did the HSC, even if I was miles ahead, I would still put in 110% at school to make sure that this was the back of my hand. Your goal should not be to be smarter than the students. It should be to be smarter than the teacher if you can, right? But be very humble about it regardless. So make sure you master this stuff, okay? All right, well, I'll leave you to it. Have a great week, and I'll see you next week. And next week, I'm going to be asking a random one of these trial questions, and I want to see who's answered which, okay? So any one of these trial questions up until checkpoint F at least, I expect you to have done. Ideally, even after checkpoint F if you can. That's all back titration, so you can read it if you'd like. Okay. All right, everyone. Have a great week. I won't hold you any longer.